Get started. Welcome to our OR Data Science Seminar Series. This is our first seminar in spring 2020. And we are very glad to have Dr. Al here today to come to visit us. And Al is the John H. Holland Distinguished University Professor and also R. Jameson and Betty Williams Professor of Engineering at the University of Michigan. And he was the founding co-director of MIDAS. Stands for Michigan Institute for Data Science, not the car repairing shop.
We don't sell mufflers.
And he is currently a section editor of the newly created Science Journal of Mathematics of Data Science. So Al is undoubtedly a national leader over the broad landscape of data science. So we are very fortunate to have him today, and let's give him a round of applause to welcome him.
I don't know. Can you hear me? Is this on?
Can you press that button?
Oh, maybe it's on mute. Is that better? Yeah, I guess I hear an echo, so that must be better. Unless this is just
someone
well-designed.
Can hear in the back?
Can you hear? Because if you're recording, of course, you're going to need this to be working, I presume.
I suppose.
Yeah. Okay. But I think it probably is. Great. Well, thank you for inviting me to Texas A&M. I haven't been here in a while. Last time was in 2013, and I've seen a lot of changes. And of course, when I was here last, it was probably about maybe 30 degrees hotter. This is more my style of temperature coming from Michigan. I'm going to talk to you today about a different point of view on machine learning AI, which focuses not on designing the next widget, the next gadget to classify or design a recommender system or a discriminator or estimate a variable, but rather to benchmark what the best possible accuracy that one can squeeze out of a data set is. And that's what benchmarking in the sense that I'm using it here. Right? So we're not trying to classify or test hypotheses. We're trying to get a handle on what is the fundamental value of the data. If the value isn't sufficiently high, given the benchmark that one extracts directly from the data, then the experimenter, the designer, the engineer can conclude I need more data or I need a different type of data to improve this type of design. So I first have to acknowledge the part of my group that contributed to this work over a period of about 8-9 years, starting with Kumar Sricharan, who's now into it. And most of this work I present today is my former student Morteza Noshad contribution, and then some of the sponsors of this work that I just look here for the sake of acknowledging them. So we're going to talk first about benchmarks in machine learning and why one should be interested in those. This leads naturally to a problem that's been around for at least 20, 30 years, which is something called divergence estimation. So it's going to turn out that the benchmarks that we're going to prescribe depend upon our ability to estimate something called a divergence or a difference between classes, between Class A data and Class B data, which can be directly related to the accuracy as measured by probability of computation error. And then we'll talk about a way to accelerate divergence estimation using a method called ensemble estimation, which is an analogous technique to boosting tagging, for people that have taken machine learning, using lots and lots of different estimators of this benchmark, combining them together like the meteorologists do in predicting the weather, multiple model aggregation. And then we'll talk about a few applications, ending with an application in what's known today as deep learning. So that's the schedule. So what do we mean by benchmark? Well, I just told you we're trying to figure out just how much information is in a data set. So we're going to focus on classification. So we have a couple of data sets, one coming from, or maybe three here, one coming from a red class, a green class, and a blue class. And one look at the data, the typical reaction is, oh, let's design a classifier and see how well it does. That'll tell us if we need more data or not, or if we have the right kind in order to make the classification of a new data point that comes in, feature 2 dimensions, right? Lies on the plane if you measure from an accelerometer, let's say, or an optical signal. It falls into this point between those classes, and the k-nearest neighbor classifier will classify that point as having a class equal to the majority class of its nearest neighbors. So that's a classifier of considerable history. It goes back at least to the 50s, when nearest neighbors were used as in the perceptron. The support vector machine classifier, which was the great revolution, Vapnik, back in the early 90s, that created this paradigm of taking the data in your feature space of 2 dimensions and expanding that data out to multiple dimensions, really high dimensions perhaps, to get rid of any nonlinearities that might occur. And this nonlinear embedding then gives you a feature space which you can define a linear separating hyperplane to classify the data. And again, you can figure out what the accuracy is, right? That classifier. And then today, we have deep networks, right, that are taking the world by storm in AI, and they're being applied to all kinds of problems in classification and learning. And again, then one can implement a classifier, CNN, convolutional neural net, and look at how well it performs. It could be overfitting, it could be model mismatch, but in the end, every conclusion that we come up with about how well any one of these does is intrinsically dependent upon the approach that you take to define the mapping of your data to a class, whether it be k-nearest majority vote, or if you're above or below a hyperplane, or if the discriminator output of a deep learning network gives you a probability greater or less than 0.5. The problem we want to solve is looking for the accuracy directly without having to introduce a new machine, right, to supplement these machines we've implemented that perhaps are giving us increasingly improved accuracy because we're increasing the complexity, the intrinsic complexity of each one of these machines is increasing over the K-NN classifier, SVM, CNN. So recently there was a new paradigm for classification called the MothNet, which is yet another paradigm that uses the sensory perceptors of a moth as a model for building networks, neural networks. Is that going to create a new revolution? I don't know. But according to this paper, the MothNet does considerably better than previous methods. So we want to sort of get some leverage on this rat race, right, of developing newer and more complex and maybe more bio-inspired ideas such as MothNets, and go directly at this. We have a time which you can look at as the number of samples available maybe on the average from all the classes, and we have the achievable accuracy that one can observe either by a human trying to do the classification by hand, on a few examples, by the latest machine learning algorithm, MothNet or some other thing that comes out. And the Bayes optimal accuracy is an accuracy that is an upper bound on what anyone can construct, either human or machine, in terms of achieving the fundamental limit, right, of the best possible classifier probability of error. And so that's our benchmark. That red dotted line is the benchmark we're trying to get at. All right, so does it make sense to even conceive of getting at a benchmark directly without defining an algorithmic model for a classifier? Well, this example is one example which shows that one can, without any assumptions on the structure of the classifier, directly get at the classifiability of a two-class problem. This is a technique that's due to Friedman and Rafsky, two statisticians, Stanford statisticians, about 30 years ago, developed this Friedman-Rafsky statistic, which is a generalization of a runs length statistic in one dimension to several dimensions to try to discriminate between the hypotheses that the green points and the blue points belong to the same distribution versus they come from different distributions. So here's pretty obvious that they probably come from two distributions, right? These features in the blue and the green are separated, and so one would assume that there's, with this number of realizations, 50 realizations, that you would at least get some interdigitation, right, of these two data sets if they were coming from the same distribution. And in this case, on the other hand, you know, maybe they do, maybe they don't. But what is certain is that if you build a minimal spanning tree, which those of you in OR know what that is, and most others should also have a notion of what that is, which is simply a graph that connects all these points in the feature space in two dimensions. Edges have length equal to the Euclidean distance between points. You build the graph that connects all the points together, but that has minimum total length. The sum of all the edges is minimized. There's always going to be n-1 edges if you have n points in this the green and blue merged class. And what this statistic does is it says, let's label all those edges according to dichotomy. So if the edge connects two red points, or two blue points, or two green points together, then we're going to eliminate that edge. If it connects two different points together, two different class points together, we're going to retain the edge. And we'll count the number of edges, dichotomous edges. And what you can see here is that the number of dichotomous edges is, in an intuitive sense, a measure of the difference, right, between the two distributions. Fewer edges if the distributions are far apart than if they're close together. And so why is this relevant? Well, it turns out that this statistic, this count of dichotomous edges in the middle of the standard tree, converges as you let the number of realizations draws from these two classes get large. It converges to a tight bound on the Bayes error, on the minimum probability of misclassification. So we haven't defined an estimator or classifier structure. We've simply looked at the points, the data points, and build a graph on those. And what we get is an estimate of the benchmark, the accuracy, fundamental accuracy achievable by any classifier if you try to classify these two classes. So that's the sort of example that motivates that this is possible. You really don't need to build a complicated or simple classifier in order to be able to estimate the accuracy limit that restricts any particular classifier's performance, the benchmark, that is. So we'll start out with just a little bit of a mathematical setting that describes classification. So we define a label 0 or 1, green or blue, Y, which has some priors, Q and P, where Q is the probability of 0, P is the probability of label 1, and the observed random variable has a distribution that depends on the class. And this is just one way of writing that distribution. Given that the class is class K, where K is either the 0 class or the 1 class, then the distribution takes on either F1 or F0. Right? So those are the two distributions that we don't know, but we have clusters of points that are labeled that come from these two that may be separated or may be interleaved. So the optimal classifier, if you did know these distributions, could be constructed, and it minimizes the so-called 0-1 loss, right? The probability of error, misclassification error. And it simply is a very intuitive classifier that says, formed from the prior distribution on the class and the distribution of the features given the class, the posterior distribution of that class given the data, given the features, right? And then feature, I should say. So for each feature now you can classify that feature according to whether it's in class 0 or class 1 by looking at the most probable label given the feature. And now, you know, the task of estimating or constructing a classifier is to get a hold of a training set and use the training set to somehow learn this probability, this posterior probability, whether that be through some particular specific model, logistic regression model, which would be one solution, or through something that's like a deep net. Okay, we're interested in the Bayes classification error rate, not in the classifier itself. So that it reduces to trying to characterize what the average misclassification error probability of this best minimum probability of error attaining classifier is. And that's the probability that the classifier label assignment C of x is not the truth, not equal to y. Right? Well, there's an integral representation of this, which is a simple representation for this epsilon function. Depends on the prior of the one class, and it depends, of course, on the distributions that are unknown, F0 and F1. But you can see it depends upon this integral of a difference. It's a weighted difference between the two distributions. So it's like a L1 difference, or what's sometimes called the total variation difference between the two classes, weighted by the probabilities of the associated labels. So an alternative representation of this is an F divergence, where an F divergence, it depends on a function g and an integral with respect to one of the distributions of one of the classes, where this g is simply equal to this quantity here. So it's a function of the u, which is a likelihood ratio between the two class densities at point of 0. And we now have an F divergence interpretation of the minimum probability of classification. That's where divergence estimation and benchmarking come together. Right? So the F divergence is a quantity that goes back to the early 60s. Imre Cesar or Silvi defined this in general for general function g, which has these properties which I'm not going to talk about, but you can get Kullback-Leibler divergence, which is one F divergence definition, Rényi alpha divergence, lots of other types of divergences by simply changing the definition of g that satisfies these properties. And instances, total variation distance, which looks almost like the exact Bayes error probability benchmark we're looking for, except for the fact it's not weighted by the prior. So this would be equal to the Bayes probability of error if the prior probability of each label was equal, right? We have equal probability of a green or a blue point being labeled, right? So alpha divergence is another, Kullback-Leibler, as I said. Another one is Hellinger-Bhattacharya divergence. There are lots of different divergences. And Henry-Penrose divergence is the limit of that count of dichotomous edges. So this is the particular divergence that characterizes that estimator or characterization of discriminability between two classes, in the example where we constructed a minimum spanning tree, and throwing away all the edges that connect points from the same class. All right, the exact F divergence is given by a generalized total variation, a divergence which includes those priors, this Bhattacharya bound. There's a lot of different methods to construct divergences. The point, though, is that learning to benchmark can be reduced to F divergence. And these bounds are important because if you can get a estimate of the Bhattacharya divergence, the Bhattacharya coefficient, then you can sandwich the achievable accuracy, right, between two functions of that coefficient. So estimating the Bhattacharya coefficient gives you a bound. What I'm going to talk about in this talk, I've done a lot of work on, over the past 10 years, on estimating various bounds. What I'm going to talk about here is an estimate that uses not a bound, but the exact divergence characterization. Okay, so this just shows the exact divergence characterization in blue, the Bhattacharya bound in green, and this minimal spanning tree construction bound, the Henze-Penrose bound in red, just shows that the Henze-Penrose bound using the minimal spanning tree is a tighter bound on the true accuracy, on the benchmark, than is the Bhattacharya bound, which is a very commonly used bound in communications and signal processing, developed in the 60s, actually before that, the Bhattacharya in the 40s. Leading to our thesis that we should be using bounds that are tight as possible, for benchmarks and not just arbitrary bounds like Monacaria or Kovac library. All right, so that takes us then to the fundamental question: how do you estimate these F divergences, right? So what do we mean by an estimate? We have data. We don't have the densities. We don't know what the densities of the underlying classes are, right? We have data. Can we use that data then to find a good estimate of the divergence, whatever divergence we've chosen, whether it be the exact Bayes error or the Penzi-Penrose or what have you. So one approach is to estimate F hat, F0 and F1, plug it in to the equation for the divergence, where you estimate them based on the corresponding outcomes, the red, the green and blue labeled points, right? You estimate F0 and F1 from those with kernel histogram or other types of methods. If you do this, we suffer this curse of dimensionality. And what the way this curse is not a computational curse. It's like Bellman's curse of dimensionality. This is a curse in terms of the accuracy, in terms of mean squared error accuracy in estimating the benchmark, estimating this divergence. And that accuracy is a function of the number of samples coming from any class. Is this accuracy, or this error, mean squared error, bias squared plus the variance square root, decays, gets better, right, as you get more samples, but it gets better really, really slowly for large dimensions. Right? D can be, for a typical application in image classification, like for the MNIST digits, D can be on the order of 1,000. Right? So this is like basically 1 over log n for large group. Optimal parametric rates, on the other hand, have a much more attractive decay. They decay as 1 over the root n, regardless of the dimension of the features, right? So here D is the dimension of the feature space that is limiting our estimates of this benchmark. So what we'd like to do is overcome this curse of dimensionality syndrome, right? And when I say overcome, what I mean is find some reasonable assumptions on the distributions, smoothness assumptions, that can take this punitively slow rate of gain in accuracy as the number of samples increases to this parametric rate. So that's the picture that shows that with ensemble estimation you can do this. If you make suitable assumptions on smoothness of the entities of each class, this is parametric rate. This is the rate that you get with any what we call base estimator, which would be a kernel estimator, for example, of that benchmark. So there's a bunch of work that I'm not going to go very quickly through that gives these achievable limits on being able to estimate divergences. And so this is a smoothness parameter over a Holder class of smoothness of densities. I don't have time to talk about that, but as this smoothness parameter gets large, the density gets smoother and smoother. Down here, your Lipschitz smooth, where S equals 1, which means you can have step discontinuities. Out here, you're smooth in terms of having lots of derivatives. D over 2 and D are the points at which D here is equal to 8. To show this, shows that particular case. And so this is the punitively slow rate that we get for D equals 8. It's on the order of n to the power of 1 over 16, negative 1 over 16. And so that's very slow rates until the smoothness gets large enough so that you can achieve parametric rates by suitable methods like convex risk minimization, which is an algebraic technique using dual optimization. Plug-in estimators are down here. You can do linear corrections. Ensemble estimators, which I'm going to talk about later, if you restrict the smoothness so it's of order d over 2, you can or greater, you can get parametric rates back, and we're going to show how you do that for a simple example in this context. So boosting is the method that one uses in order to improve performance when one has lots of different estimators. So the fundamental idea behind this ensemble estimator is going to be to use a bunch of base estimators, a bunch of kernel estimators, the distribution, all with different kernel widths. So different resolutions on the estimate, the bumpiness of your distribution. You use them all, and then this then gives you an estimate of the divergence for each one of the widths of the kernel from L1 to L, from L1 to L, and then you combine them with some linear combination of coefficients, W0, L, to get a ensemble averaged estimator. And this is the boosting concept where the weights are computed according to some algorithm that typically depends upon the data, like with data boost. For those who are familiar with boosting classifiers, Freund and Shapiro, data boost methods. What the alternative that we are achieving with this talk and with the papers that, paper 3 in particular, was published just a year and a half ago, is that these weights are data that we can plug in to get parametric rates, that is to get acceleration from punitively poor, almost logarithmically slow convergence back to the best parametric convergence, that is 1 over root n. The weights required to achieve that with kernel density estimates or k-nearest neighbor or locality sensitive hashing estimates, which I'm going to talk about in a minute, can be computed. Those weights are offline. They don't depend on the data. You can still achieve these rates. That's important because it means that we don't have to have the computational burden of updating the weights as a function of the data as it comes in. Because it's offline and you're guaranteed to get optimal weight. So locality sensitive hashing is the simplest, arguably. It is oversimplification, right, of an estimate of a divergence, because it boils down to using a binned histogram estimate of F0 and F1, where F0 is in blue and F1 is in red, generating these points. And then the divergence is basically a plug-in with Ni over N. That's the cell count, the average number of red or blue points that lies in a particular bin, the cell of the histogram, and you plug that in as an estimate of the histogram, which we call NI, the red point count, and MI, the blue point count in the I cell. And then I only have I don't have all of the tiling of the two-dimensional, right, D equals 2 feature space here, because for these other tiles, these other bins, we only have red points, no blue points, which would cause this to explode. So we just throw those away. That's why I say overly simplistic, heuristic, ad hoc, whatever you want. Poor estimator, weak estimator. Those who are familiar with Freud and Shapira's work, they also refer to boosting as boosting weak estimators. So what we're going to do is we're going to take various histogram widths on the cells that are going to be scaled appropriately so that we get the best possible estimator variance. And each one of those widths is going to give us a different kernel estimate. And we'll combine them all together and be able to achieve far better accuracy on the benchmark than if we used any one of these widths alone, which is this punitive, almost logarithmic, bad accuracy. So I'm not going to go into the details here, but the locality sensitive hashing plugin estimator you can derive bias and variance, closed form, up to an order of 1 over n times the resolution, the side, length of the side of one of those bins, raised to power d equal to the feature dimension. And so the CIs are what capture the distribution, capture the g, the function that we're using in the divergence. That's the bias, and that's the variance, which decays as 1 over n. We can choose now epsilon, the width of a histogram, as a particular function to make this remainder term equal to 1 over root n, which is the rate we want, right? That's what we want in terms of our bias, because the bias squared plus the variance, square root of that sum, is equal to that root mean squared error that we want to be equal to 1 over root n. Right? So if we choose, we want the remainder term on this to be 1 over root n in order to be able to get that. So if you choose epsilon equal to this quantity, so it's going to decrease very slowly as a function of the dimension, d, and then as a function of n. So slowest term of the bias decay rate, if you do this, make this choice, is the leading term here, I equals 1 to d of epsilon to the I, epsilon being equal to this order, you get back to this punitively bad rate, right? By using ensembles, we're going to find a set of weights so that with different scale factors in front of this epsilon, we can sum over the bias by summing the ensemble summing the estimators of divergence, and knock out successively each one of these high rate terms without knowing what CI is. That's the key. Right, so that's the ensemble method. You apply the weights to the ensemble, weights to each one of these divergence estimates with a particular epsilon kernel width, and that estimator is simply a linear combination. The ensemble estimator is a linear combination of each one of those width-specific estimates, weighted by Wj. The bias is equal to this a term where the sum over these L different widths on this ensemble estimator commutes with the sum over the dimension that I, for the first order to dth order series expansion that was used to get that bias expression, and only affects where T, Ji is the parameter that characterizes epsilon. Right? Epsilon is equal to t n to the minus 1 over 2d. So if we can define the wj's so that this quantity is equal to 0, t is just some numbers, right? Some numbers that we select on the scale of the width. Then we can knock out this entire leading term, and we end up with order 1 over root n. So this is a set of L equations and L unknowns, the weights, and that leads to a system that is a linear system of equations. So we could find the solution W1 to WL in the null space of this matrix, right, in order to zero out that higher order, slow converging terms in the bias. So Chebyshev methods can be used to design these scale factors for each one of the L kernel estimates of width parameter, which I don't have time to talk about, but there's a Chebyshev function approximation can be used to basically form the design for this matrix so that we have the most stable solution as a function of variations in the number of ensemble L, right, estimates. So variance is on the order of a quadratic in the weights. It simply follows from the form of the weighted ensemble estimator. W transpose times the vector of these multi-scale kernel estimates of the divergence. So that's W transpose the covariance times W. And if that covariance has an eigenvalue which is equal to lambda max, then this can always be bounded up above by the norm, L2 norm of W squared. And now we have a optimization problem that can be done completely offline to solve for the weights that simultaneously achieve low variance and zero out bias terms. So L has to be greater than D in order for this solution to exist. Right. And this ensures the mean squared error is now of 1 over n. That is, the root mean squared error is the parametric rate. So I just show this multi-class classification application where we have our benchmark learner is here in blue. We don't know the model. The benchmark doesn't know the model. We've constructed this as a 4-class model, concentric sphere regions characterize the classes, so it's not linearly separable. For each of the 4 classes, a nested sphere, right? Difference, spherical difference from the center sphere to the set difference of spheres that contain the center sphere and then successively contain that sphere and so forth. And so it's over 20 dimensions. And so we implemented here a deep neural network with 4 layers, ReLU and Atom and so forth as methods, as activation functions, and the methods for estimating the gradient from backpropagation. And so you have then all of these accuracies by implementing boosting methods. XGBoost is a method for classification. We're not estimating the accuracy here in the green curve. We're using a boosting classifier, deep neural network, random forest, and so forth. And the benchmark says the following. It says that we have a substantial margin of improvement. If we could improve if we had less than, say, 3,000 samples, then we can improve the accuracy by a substantial margin relative to deep neural. With the data that is available from the realization of this 4-class problem. Another application is to figure out a stopping rule. How many data points is sufficient if you're using a stochastic gradient descent, for example, which is successively choosing samples in your data set. How many are sufficient to know that you're close enough to benchmark that you can stop your iterations? So the benchmark learner in blue would tell you can stop at about 850 iterations of the stochastic gradient descent. MNIST, this just shows again, for the MNIST data set, we get a 14% error rate from the benchmark learner. And so that means there's still about 6% or 7% left relative to the best available, as of 2013 anyway, learners that machine learning algorithm can classify digits in the MNIST data set. Okay, so I want to terminate this. How much time do I have? Like 4 minutes? Okay, so just on a quick example of applying this benchmark learning to deep neural nets to characterize the information bottleneck. I'm not going to cover this in any detail, but the slides, I think I can give them to you and they can be posted. But the fundamental questions about deep neural nets is that we have a remarkable empirical performance evidence, but we don't really understand to a sufficient degree why they work. There's hypotheses. One of the hypotheses is called the compositional learning hypothesis, which says that DNNs learn in 2 phases. They first memorize on all the easy cases in the 2 classes. They memorize patterns, the easy to classify patterns in the 2 classes. And then they generalize to the hard cases. That is, they go through a compression phase in phase 2. And so this phase 1, phase 2, over a deep learning structure such as this one here I'm showing, with an input layer and 4 intermediate layers and an output layer, logistic layer, multi-layer perceptron. So all layers are connected. All layers are completely connected to the previous ones. This characterizes layer by layer as a function of time. Time starts here in terms of training, the compression versus memorization plane. And I'm not going to explain any more than just to say that this is a very common method today of characterizing these memorization versus compression characteristics of deep neural nets, and that this characteristic convex structure between the compression plane and the compression axis and the discrimination axis was held by Naftali Tishby as confirming this compositional hypothesis, that you start out by learning the easy cases and then compressing. So compression goes back this direction. So what we showed is that if you use our method for estimating divergence, mutual information being used here as the compression plane quantity, that you can do much better in terms of estimation performance. Accuracy in red and orange is our ensemble estimator of mutual information for each of these layers. And then what's in green and blue are the much noisier are the estimates that are used in Tishby, Shai-Schwartz paper, and basically confirming this compositional hypothesis with a much better. We use 2 meta-learning concepts. The first is we are learning ensembles, so you're learning ensembles of learners. And the second one is that we're learning how difficult the learning problem is, right? The second meta-learning problem is learning the Bayes error rate. We can use this ensemble method that we introduced to achieve rate optimal performance, and we can apply this to many different problems in learning to benchmark. So that's all I really have to present today. So thank you for listening.
Overfitting, just like when we learn the examples that you learn both weak learners and the example weight from data, how you would avoid the overfitting issue?
Yeah, so here what we have to keep in mind is that we're not learning over a feature space a set of coefficients of a deep learning network or a SVM, right? So we're not learning a large dimensional quantity. What we're learning is a one-dimensional quantity. Right? So it's the benchmark. And the point is that the weights that are used in the ensemble learning are computed offline. So there's no generalization error there. Right? You're not overfitting because those are computed based on the Chebyshev polynomial solution, stabilizing solution of the linear set of equations that I showed. So the problem of overfitting is really, really bad when you're trying to estimate high dimensional quantities, right? Like coefficients of some classifier. But now if you turn the problem on its head, such as we're doing here, and say we're not interested in the classifier, this high dimensional problem, we're just interested in estimating the performance. We're just one scalar quantity. This overfitting problem is much less of a problem.
Yeah, I got what you mean. And another question, if I may. So I'm trying to think what's the practical guidance value for like practitioners in like the deep learning field. So does it mean that like for image, I'm not quite sure how this is generalizable to very large and potentially noisy data set and potentially not even IID data set like ImageNet. So for example, if I do a real image classification rather than MNIST, using this to predict error rate, and if it's lower than the ever achieved error rate by all past models, does it mean that I could continue working on this data set without being worried about overfitting?
You stated it better than I could have. Yes, that's exactly what this tells you. In the case, these methods allow you to leapfrog over this rat race that I referred to in the beginning of being on the treadmill to develop more and more sophisticated learning methods and worrying about overfitting and so forth. Right? So by aiming at estimating performance directly, you can, at the very least, define a horizon that you cannot go beyond, right? Up to some confidence interval, depending on the size of the data set.
Very cool. Thank you for explaining.
So I have a question here. When you have the method to estimate this error performance bound, does that immediately imply what kind of method you can devise, or does that easily imply some method you can develop achieve that performance?
That's the holy grail. Yeah, I mean that would be fantastic if you could extract information from these bounds that tell you something about how to achieve them. But as in many cases of engineering systems, going from bounds to practical applications directly, with practical algorithms, is very difficult. Claude Shannon defined his bound on the maximal rate that you could push through a channel of limited bandwidth, channel capacity, back in 1948. It took 50 years for turbo codes to come out to show that there's an algorithm that can actually achieve this rate. So those turbo codes were not guided at all by Shannon's construction of his bounds. Random, random construction using typical sequences. And, that didn't yield any insight into how to achieve them. There are two separate problems, and it's for that reason that in response to this gentleman's question, that you can sidestep this overfitting problem if you focus on accuracy. But if you try to turn that around and specify an algorithm that'll change that accuracy, I think there's probably some fundamental, like Heisenberg uncertainty principle or something lurking there that says you can't do it. Right? But I don't want to be so negative.
Right, I follow-up question. So for the bound, you provide the insight because of the way you can calculate the bound so close to the true bound, true error rate. It's because of you eliminate that slow conversion, the bias reduction part.
Right.
Now, by looking at the practical, like the CNN method, DN method, and perform better than the other method, does that imply the DN actually does that error reduction more efficiently than the other method?
Possibly.
Although we don't know for sure.
We don't know for sure. We do know that the bias is smaller, right? Because the variance bars along the DNN and SVM and so forth, which I didn't show in that plot, are pretty much of the same order. So the gain is virtually 100% due to a decrease in bias. So somehow DNNs are moving towards a reduction in bias, and eventually perhaps matching these fundamental benchmarks that can be determined from data. Yeah.
Any other questions? Well, if there's no other questions, I'd like to present a small token appreciation to our hero for coming.
Thank you so much.
Okay. Thank you.
Thank you for coming and listening.